All right, so let's take a look at a nerve impulse, also known as an action potential. All right, so what do we start off with? And one of the things I wanted to point out to you before we get started here is that when we take salt into our body, the salt doesn't stay salt. All right, so if we take sodium chloride into our body, it's going to separate in the water into sodium ions and chloride ions. So we see sodium ions here, there's a chloride ion right there. All right, the same thing happens if we take a different kind of salt called potassium chloride in. Won't stay potassium chloride, it will separate into potassium ions, all right, shown here, and chloride ions shown there. All right, so this is what happens when we take these different kind of salts into us. All right, so we have to think about what's in our body here is not salts as one thing, but ions in our body because we are mostly water. Okay, so this is looking at what is known as the resting potential. So this is a charge difference between the plasma membrane, this is a charge difference across the plasma membrane of a neuron here. So here the plasma membrane is polarized, meaning it has one charge on one side of its membrane and a different charge on the other side. Okay, so let's look at the outside of the plasma membrane. So outside of the plasma membrane, we have a large number of sodium ions, which is shown here in pink, and very few potassium ions shown there in purple. But because of all these positively charged ions outside of the plasma membrane of a neuron, this outside of the plasma membrane is positive. If we look inside of the cell or inside of the plasma membrane, we see we have a lot of potassium ions inside here, all right? And we have few sodium ions in here, all right? But we also have, and they're not showing a lot of these, but we also have a large number of negatively charged proteins inside of the cell. And so what that does is it makes inside the cell negative, all right? So positive outside, a lot of sodium outside the cell, positively charged outside the cell, a lot of potassium ions, but because of these negatively charged proteins inside here, inside is negative, all right? Now maintenance of this. How do we maintain these sodium ions out, potassium ions in? Is through this thing right here. And this is known as a sodium-potassium pump. And what it does is it pumps sodium out of the cell and potassium into the cell. And this thing works all the time, all right? If you want to know technically, it pumps 3 sodium out for every 2 potassium in, okay? So what we have done here is we set up a situation where we have a high amount of sodium outside the cell, little sodium in, high amount of potassium inside the cell, few potassium out. So what's going to end up causing this an action potential or a nerve impulse to occur is just the diffusion of ions. All right, so before that can occur, what we have to have is some stimulation above what is known as our threshold potential. So a threshold potential, this is a stimulation level that must be exceeded to cause a nerve impulse or a muscle contraction, all right? So, if you've ever been outside on a warm day and you look down at your leg and there's a mosquito feeding upon you, well, that mosquito had to land on you. It had to stick its proboscis, that's what it's called, its proboscis into you to start sucking your blood, all right? Now, all those things were below threshold. You didn't feel it, all right? Sometimes you do, if that mosquito is unlucky, it lands on a direct nerve ending, that could be above threshold and you would feel that. Okay, so let's look at an action potential. So let's go to this picture. This shows this at resting potential, sodium out, potassium in, positive out, negative in. We go to the next picture here, shows the same thing, sodium out, potassium in, positive out, negative in. Okay, so now we're going to get an impulse above threshold. And what we're going to get is a depolarization of the plasma membrane. So depolarization is loss of electrical charge on the surface of a membrane. So what's going to happen here is we get stimulation above threshold. That's going to cause these sodium ion channels to open. And what's going to happen next is that sodium simply diffuses into the cell. All right? So we see that here, right? So let's just review just for a second here. Go to this picture. Sodium out, so this is at resting potential. Sodium out, potassium in, positive out, negative in. We get these positive ions coming in. Positive ions coming into this negative area. That's going to neutralize that membrane. So this influx of positive ions into the cell is going to neutralize that plasma membrane. Now this is quickly followed by what is known as repolarization. So repolarization is the movement of the membrane potential to its initial resting state, meaning it becomes polarized again. All right? So when sodium ion diffusion slows down, this is going to cause the potassium ion channels to open. And this allows potassium to simply diffuse out of the cell. All right? So if we go to this picture here, this was all neutral area back here. Here it's neutral. And so we're going to take some positive ions and move it into a neutral area. That area becomes positive. If we remove positive ions from a neutral area, that area becomes negative. All right? So the movement of these positive ions outside the cell makes outside the cell positive again, makes inside the cell negative again. All right? And these changes in charge across a membrane are going to power an impulse. So this is what an action potential is. So an action potential or nerve impulse is a rapid sequence of depolarization and repolarization along a nerve cell membrane. Okay? So we're going to go from polarized, positive, sodium out, potassium in, positive out, negative in, to depolarized, sodium diffuses in, neutralizes the membrane, to repolarizing, potassium diffusing out, so now positive out, negative in. All right? Now, there's a problem here. So when a neuron is like this, we're going to have this small refractory period. This is a period of resistance to stimulation. So when the plasma membrane is like this, if another impulse hits it, nothing will occur. Okay? So we have to get this to go back to looking like this. In order to do that, we have to use the sodium-potassium pump. All right? So the sodium-potassium pump is going to make this look like this again. All right? And this is why there's such a high metabolic cost to all of our nerve impulses. Anytime we have a thought process, anytime we have, whether that is conscious or unconscious or any movements, this is going to expend a lot of energy because sodium diffuses out, potassium diffuses in, and then we have to restore that to look back like this, and that's going to cost some energy every time. Okay, so let's look at signal conduction of these nerve impulses. All right, so propagation of an action potential. If we have an action potential in one area, it's going to cause action potentials in adjacent areas. All right? So if we have an action potential here, it's going to cause an action potential there, which then causes an action potential there, and so on. Now, typically, action potentials move in one direction because they go from dendrite to cell body through the axon. Okay? So a way to think about this is kind of a domino effect. You hit a domino, it knocks all the rest of them down in a row. Now, let's look, so this shows it again here. So this is showing that refractory period that we talked about. Now, the importance of myelin, all right? So if we look at this cell here, this cell has no myelin on it. So whenever we have a myelinated area, it's going to conduct impulses over the entire plasma membrane surface, what is known as continuous conduction. And that's just like what I talked about. We have an impulse here, which causes an impulse there, which causes an impulse there, which causes an impulse there, and so on. All right? In myelinated areas, so showing this, here we have some Schwann cells. All right? So myelin is an insulator, and it does not allow an impulse in that area. But between Schwann cells, or oligodendrocytes, are these little areas called nodes of Ranvier. All right? And nodes of Ranvier are these small unmyelinated spaces that can conduct an impulse. So what happens in here, in a myelinated area, instead of that impulse, if we go to this next picture, it shows this here, instead of that impulse moving from here to here to so instead of it moving from here to here to here to here to here and so on, it's going to skip from this node to that 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 node. So let's think about this. So instead of going from here to here to here to here, it goes from here to here to here to here. So you're way over here where you would be over here. So by skipping from node to node, that impulse moves a lot faster in these myelinated areas. Okay? So, and I just want to show, these are exaggerations of these nodes. All right, if I go to this picture here, this is showing a Schwann cell here and a Schwann cell there, and that little brown, little line there is showing a node of Ranvier, just right there. All right. Now let's look at the all or none response. So here, a neuron responds completely or not at all to stimulation. All right. So you either get above threshold, you have a stimulus, or you have an impulse, or it's below threshold and nothing. So the greater intensity of a stimulation, whether you're talking about more pain or more pleasure, right? This has to do with more impulses per second. So, if you stub your toe and it hurts a little versus stubbing your toe and it hurts a lot, when it hurts a lot, you're sending a lot more impulses per second than when you hurt it just a little.